In the grand theatre of physics, two towering theories stand as monuments to human understanding, yet they refuse to shake hands. On one side sits general relativity, Albert Einstein's masterpiece from 1915, which describes gravity not as a force, but as the very curvature of space and time itself. Picture a bowling ball placed on a stretched rubber sheet, causing smaller marbles to roll toward it. This elegant theory has guided us to discover black holes, predict the expansion of the universe, and even detect gravitational waves rippling through the cosmos, like whispers from colliding neutron stars, billions of light years away. On the other side stands quantum mechanics, the strange and counterintuitive framework that governs the microscopic realm. Born in the early 1900s through the work of Max Planck, Niels Bohr, Werner Heisenberg, and others, quantum theory reveals a reality where particles exist in multiple states simultaneously, where the act of observation changes what we observe, and where the universe operates on probabilities rather than certainties. This theory has given us lasers, computer chips, magnetic resonance imaging, and countless other technologies that define modern life. Yet despite their individual successes, these two pillars of physics have remained stubbornly incompatible for over a century. General relativity works magnificently on large scales, from planets orbiting stars to the evolution of entire galaxies. But it treats space and time as smooth, continuous fabrics. Quantum mechanics excels at describing atoms, subatomic particles, and the forces between them, but it assumes space and time form a fixed, unchanging backdrop against which quantum dramas unfold. The problem becomes acute when physicists try to understand situations where both theories should apply simultaneously. What happens inside a black hole where gravity becomes so intense that quantum effects near the event horizon cannot be ignored? How did the universe behave in its first moments after the Big Bang, when all matter and energy were compressed into a space smaller than an atom, making both gravitational and quantum phenomena equally important? These questions demand a unified theory, a quantum theory of gravity that has eluded the brightest minds for generations. At the heart of quantum mechanics lies one of its most mysterious and profound features: quantum entanglement. This phenomenon occurs when two or more particles become connected in such a way that measuring one instantly affects the others, regardless of how far apart they may be. Einstein famously called this spooky action at a distance, because it seemed to violate the principle that nothing can travel faster than light. He believed that quantum mechanics must be incomplete, that there must be hidden variables determining the outcomes we observe. But Einstein was wrong about entanglement, though brilliantly wrong in a way that advanced physics immeasurably. In 1964, physicist John Bell proved that no theory based on local hidden variables could reproduce all the predictions of quantum mechanics. Subsequent experiments, beginning with those of Alain Aspect in the 1980s and continuing with increasingly sophisticated tests today, have confirmed that entanglement is real. Two particles can indeed share a quantum state, such that measuring one immediately determines properties of the other, even if they are separated by millions of kilometers. This non-local nature of entanglement presents a fascinating puzzle when considered alongside gravity. If entangled particles remain connected across vast distances, and if gravity affects everything in the universe, might there be a deep connection between these two phenomena? Could the fabric of space, time itself, emerge from a vast network of quantum entanglements? Or perhaps gravity could create entanglement between particles that have never directly interacted? These questions have moved from the realm of speculation to serious scientific inquiry. The idea that gravity and entanglement might be fundamentally linked has captured the imagination of theoretical physicists and sparked a revolution in how we think about the nature of reality. Some propose that wormholes, those hypothetical tunnels through space-time, might be equivalent to quantum entanglement in ways that could unify our understanding of gravity and quantum mechanics. The stakes could not be higher. If gravity and entanglement are truly connected, it would represent the most significant advance in fundamental physics since the quantum revolution began over a century ago. Such a discovery would not only solve the puzzle of quantum gravity, but could also reveal that space, time, matter, and energy are all emergent properties of something even more fundamental, an underlying quantum information structure that weaves together the fabric of existence itself. Consider the profound implications. Every black hole in the universe might be connected to distant regions of space-time through quantum entanglement. The expansion of the cosmos might be driven not just by dark energy, but by the growth of entanglement networks spanning galactic superclusters. Even the arrow of time, the reason we remember the past but not the future, might emerge from the way entanglement evolves and spreads throughout the universe. Yet for all the excitement these ideas generate, we must remember that science advances through evidence, not just elegant mathematics or compelling intuition. The connection between gravity and entanglement remains largely theoretical, supported by sophisticated calculations, but not yet confirmed by definitive experiments. The challenge lies in testing these ideas in a universe where gravity is extraordinarily weak compared to other forces, and where quantum effects typically vanish at the scales where gravitational phenomena become obvious. This weakness of gravity presents both a blessing and a curse for physicists. On one hand, it allows us to live in a universe where atomic matter can exist without being crushed into black holes, where planets can maintain stable orbits, and where the delicate chemistry of life can unfold. On the other hand, it makes experiments that probe the intersection of gravity and quantum mechanics extraordinarily difficult to perform. To put gravity's weakness in perspective, consider that it takes the entire mass of Earth to hold a feather to the ground, while a small magnet can easily overcome Earth's gravitational pull to lift a paperclip. The electromagnetic force that powers the magnet is roughly 10 to the 37th power times stronger than gravity. This vast difference in strength means that gravitational effects on quantum systems are typically so small as to be undetectable with current technology. Nevertheless, ingenious physicists have proposed experiments that might reveal gravitational effects on entangled particles, or detect entanglement created by gravity itself. These tabletop quantum gravity experiments represent humanity's best hope for testing whether the deepest mysteries of physics are connected in ways that could transform our understanding of reality. The journey ahead will take us from the mathematical abstractions of theoretical physics to the cutting-edge laboratories where scientists attempt to measure the unmeasurable. We will explore black holes where space-time curves so severely that quantum mechanics and gravity collide, investigate proposals for experiments that might detect gravity's influence on quantum entanglement, and consider what it would mean for human civilization if these connections prove real. But first, we must understand each player in this cosmic drama separately before we can appreciate how they might dance together. The story of gravity and entanglement is not just about particles and forces, fields and waves. It is about humanity's relentless quest to understand the deepest workings of nature, to find the hidden connections that bind together everything from subatomic particles to galaxy clusters into one magnificent, interconnected whole. As we stand at the threshold of potentially revolutionary discoveries, we find ourselves in a position similar to physicists in the early 1900s, when the classical certainties of Newton's clockwork universe gave way to the strange new realities of relativity and quantum mechanics. The universe revealed then that it was far stranger and more beautiful than anyone had imagined. Now, as we probe the possible connections between gravity and entanglement, we may be on the verge of discoveries that will once again transform our understanding of existence itself. The questions before us are not merely academic exercises for physicists to ponder in their offices and laboratories. If gravity and entanglement are linked, it could eventually lead to technologies we can barely imagine, from quantum computers that harness the curvature of space-time to communication systems that operate through the quantum structure of reality itself. More immediately, it promises to finally answer some of the deepest questions humans have ever asked about the nature of space, time, matter, and the forces that govern the cosmos. The stage is set for one of the most important scientific investigations of our time. Two of nature's most fundamental phenomena, separated by vast differences in scale and behavior, may be secretly connected in ways that could revolutionize physics. The story of how scientists are working to uncover these connections and what it might mean if they succeed begins with understanding each phenomenon in isolation before exploring their potential unity. To understand how gravity might connect to quantum entanglement, we must first appreciate just how revolutionary Einstein's description of gravity truly is. Before 1915, gravity was understood through Isaac Newton's law of universal gravitation, formulated in 1687. Newton described gravity as a force of attraction between masses, acting instantaneously across any distance. This picture worked beautifully for centuries, guiding astronomers to predict planetary motions, discover new worlds like Neptune, and launch spacecraft with pinpoint precision. But Newton himself was troubled by his own theory. How could objects exert forces on each other across the void of empty space without any physical mechanism connecting them? He famously wrote, "I frame no hypotheses about the cause of gravity," acknowledging that his mathematical description, however accurate, left the fundamental nature of gravitational attraction mysterious. Einstein's stroke of genius was to realize that gravity is not a force at all, but rather a manifestation of the geometry of space and time themselves. In his general theory of relativity, massive objects do not pull on each other through some mysterious action at a distance. Instead, they warp the fabric of space-time, and this curvature guides the motion of other objects along what mathematicians call geodesics, the shortest paths through curved space-time. Imagine an ant walking on a curved surface like a sphere. From the ant's perspective, it is walking in a straight line, but an observer watching from outside the sphere sees the ant following a curved path around the surface. Similarly, Earth orbits the Sun not because it is being pulled by a gravitational force, but because it is following the straightest possible path through space-time that has been curved by the Sun's mass. This geometric interpretation of gravity immediately resolved Newton's conceptual difficulties. There is no mysterious action at a distance because gravity is not transmitted between objects. Instead, each massive object curves the space-time in its immediate vicinity, and this curvature propagates outward at the speed of light, creating what we observe as gravitational effects. The mathematical framework Einstein developed to describe this curved space-time is based on Riemannian geometry, a branch of mathematics that deals with curved surfaces and higher dimensional spaces. The central equation of general relativity connects the curvature of space-time on one side with the distribution of matter and energy on the other. In the elegant words often used to summarize Einstein's theory, matter tells space-time how to curve, and curved space-time tells matter how to move. This seemingly abstract mathematical theory has been confirmed by countless observations and experiments over the past century. General relativity predicted that massive objects should deflect light rays passing near them, an effect dramatically confirmed during a solar eclipse in 1919, when stars appeared slightly displaced from their usual positions due to the sun's gravitational influence. The theory also predicted that gravity should slow down time, an effect now routinely measured with atomic clocks and essential for the accuracy of global positioning system satellites. Perhaps most remarkably, Einstein's theory predicted phenomena that were not observed until decades after his death. Black holes, regions where matter has collapsed to such density that space-time curves back on itself, were first proposed as mathematical curiosities in the 1960s. Today, we have direct images of black hole shadows and have detected the gravitational waves produced when black holes merge, exactly as general relativity predicted. The theory also revealed that the universe itself is not static, but must be either expanding or contracting. Einstein initially resisted this conclusion, adding a cosmological constant to his equations to allow for a static universe. When observations by Edwin Hubble in the 1920s showed that distant galaxies are indeed receding from us, Einstein called the cosmological constant his greatest mistake. Ironically, modern observations of accelerating cosmic expansion suggest that something very much like Einstein's cosmological constant, now called dark energy, does dominate the universe's large-scale dynamics. Yet for all its successes, general relativity faces a fundamental limitation when confronted with quantum mechanics. Einstein's theory treats space-time as a smooth, continuous manifold, like a perfectly flexible rubber sheet that can be stretched and curved but never torn or punctured. This classical description works magnificently at macroscopic scales, but quantum mechanics tells us that at the smallest scales, around the Planck length of 10 to the minus 35 power meters, quantum fluctuations should make space-time itself uncertain and probabilistic. At such scales, the very notion of a smooth geometric background breaks down. Space-time should foam and fluctuate, with virtual particles and antiparticles constantly appearing and disappearing, creating and destroying tiny wormholes and bridges between distant regions. This quantum foam represents a regime where general relativity simply cannot apply in its current form, because the theory assumes the existence of a well-defined geometric background that quantum mechanics says should not exist. The problem becomes acute in situations involving both strong gravity and quantum mechanics simultaneously. Inside black holes, matter is crushed to densities where quantum effects become important. Yet the gravitational field is so strong that space-time curvature dominates the physics. Near the moment of the Big Bang, the entire observable universe was compressed to a size smaller than a proton, making both gravitational and quantum phenomena equally significant. These extreme conditions demand a quantum theory of gravity, but constructing such a theory has proven extraordinarily difficult. Unlike the other fundamental forces of nature, the electromagnetic force, the weak nuclear force, and the strong nuclear force, gravity has resisted all attempts at quantization using the standard techniques that worked so successfully for the other interactions. The root of the difficulty lies in gravity's unique relationship with space and time. The other forces act within a fixed space-time background, like actors performing on a stage. But gravity is the stage itself, the very arena in which all physics takes place. When we try to quantize gravity, we are essentially trying to make the stage itself uncertain and probabilistic, a conceptually challenging undertaking that has no parallel in other areas of physics. One approach, called canonical quantization, attempts to apply quantum mechanics directly to Einstein's equations, treating the geometry of space-time as a quantum mechanical system with wave functions and uncertainty relations. This leads to the Wheeler-DeWitt equation, sometimes called the equation for the wave function of the universe. But solving this equation has proven nearly impossible, except in the simplest cases. Another approach, known as loop quantum gravity, suggests that space-time itself is not continuous, but is made up of discrete, indivisible units at the Planck scale. In this picture, space-time has an atomic structure, with fundamental loops and nodes connected in a vast network that gives rise to the smooth geometry we observe at larger scales. This approach has had some success in addressing specific problems, such as resolving the singularities that appear at the centers of black holes in classical general relativity. String theory takes a radically different approach, proposing that the fundamental constituents of nature are not point-like particles, but tiny vibrating strings existing in 10 or 11 dimensions. In string theory, gravity emerges naturally as one of the vibrational modes of these strings, potentially providing a unified description of all forces including gravity. However, string theory requires extra dimensions beyond the four we observe, and it has proven difficult to make testable predictions that distinguish it from other approaches. A third major approach focuses on the holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary surface, like a hologram. This principle emerged from studies of black hole thermodynamics and has led to remarkable insights, such as the ADS-CFT correspondence, which establishes a precise mathematical relationship between certain theories of gravity and quantum field theories without gravity. Each of these approaches to quantum gravity offers different insights, but none has yet provided a complete, experimentally confirmed theory. The challenge is partly observational, because the energy scales at which quantum gravitational effects become important are far beyond what we can reach with current technology. The Planck energy, where quantum gravity effects should become apparent, is about 10 to the 19th power times larger than the energies available at the Large Hadron Collider, the world's most powerful particle accelerator. This enormous energy gap means that tests of quantum gravity must rely on either extremely sensitive measurements of very weak effects or observations of extreme astrophysical environments where such energies might naturally occur. Black holes, neutron stars, and the cosmic microwave background radiation left over from the Big Bang represent some of our best laboratories for probing quantum gravitational phenomena. The weakness of gravity compared to other forces also creates both opportunities and challenges for understanding its quantum nature. On one hand, this weakness means that gravitational effects on quantum systems are typically negligible, making them extremely difficult to detect. It takes exquisite experimental precision to measure how gravity affects the quantum states of particles, atoms, or even small objects. On the other hand, gravity's weakness means that it couples very gently to quantum systems, potentially allowing for delicate quantum effects to survive in gravitational environments where they might be destroyed by stronger interactions. This gentleness opens the possibility of using gravity as a tool to probe and manipulate quantum systems in ways that other forces cannot. Recent theoretical work has suggested that gravity might play a surprising role in creating and maintaining quantum entanglement between particles that have never directly interacted. If two masses are placed in quantum superposition states, their gravitational fields would also be in superposition, potentially entangling other quantum systems through purely gravitational interactions. Such gravitationally induced entanglement would provide a direct bridge between the classical world of general relativity and the quantum realm. The possibility of detecting such effects has motivated proposals for increasingly sensitive experiments designed to measure gravitational influences on quantum systems. These include attempts to put small objects containing perhaps billions of atoms into quantum superposition states while monitoring how their gravitational fields affect nearby quantum sensors. Such experiments push the boundaries of both quantum control and gravitational measurement, requiring technologies that are only now becoming available. Understanding gravity's relationship to quantum mechanics is not just an academic exercise. Gravity affects every object in the universe, from subatomic particles to galaxy clusters. And if quantum mechanics provides the fundamental description of nature, then gravity must ultimately have a quantum description as well. The search for this description has already led to profound insights about the nature of space, time, and information that extend far beyond physics into philosophy and our understanding of reality itself. As we prepare to explore how quantum entanglement might connect to gravity, we must keep in mind both the extraordinary success of Einstein's geometric description of gravity and its limitations, when quantum effects become important. The smooth space-time of general relativity may be an approximation, valid at large scales, but giving way to something far stranger and more wonderful in the quantum realm, where space and time themselves become uncertain and probabilistic. If gravity represents the most familiar yet geometrically revolutionary force in physics, quantum entanglement embodies the most counterintuitive and philosophically challenging phenomenon in all of science. To understand how these two seemingly disparate aspects of nature might be connected, we must first confront the strange reality of quantum entanglement and the profound questions it raises about the nature of reality itself. The story begins in 1935 with a thought experiment proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen, forever known as the EPR paradox. These physicists were deeply troubled by what they saw as an unacceptable implication of quantum mechanics. According to the theory, when two particles interact and then separate, they can remain connected in such a way that measuring one instantly determines properties of the other, regardless of the distance between them. Einstein and his colleagues argued that this apparent instantaneous connection violated the principle of locality, the reasonable assumption that objects are only directly influenced by their immediate surroundings. For information about a measurement on one particle to instantly affect another particle light years away would seem to require faster than light communication, violating one of the fundamental principles of Einstein's own theory of relativity. The EPR paper proposed what seemed like a more reasonable explanation. Perhaps quantum mechanics was incomplete, they suggested. Maybe the particles carried hidden information, predetermined values for all possible measurements that had been established when they first interacted. When we measure one particle and find it spinning clockwise, for example, we are not causing the other particle to spin counterclockwise. Instead, we are simply discovering information that was already there, hidden variables that determined the outcomes of all possible measurements from the moment the particles first became correlated. This hidden variable interpretation seemed to restore common sense to quantum mechanics. It eliminated the need for mysterious instantaneous connections between distant particles and preserved our intuitive understanding of reality as consisting of objects with well-defined properties that exist independently of observation. For nearly 3 decades, many physicists found this explanation compelling, even though it contradicted the standard interpretation of quantum mechanics. The resolution came in 1964 through the brilliant work of physicist John Bell, who proved that any theory based on local hidden variables must satisfy certain mathematical constraints, now known as Bell inequalities. More importantly, Bell showed that quantum mechanics predicts violations of these inequalities in specific experimental situations. This meant that experiments could definitively test whether nature operates according to local hidden variables, or truly exhibits the non-local correlations predicted by quantum mechanics. Bell's theorem represents one of the most profound results in the history of science because it shows that certain philosophical assumptions about reality are not just untestable, but actually false. Either the world is fundamentally non-local, with measurements on one particle instantly affecting distant particles, or it is not realistic in the sense that particles do not have definite properties independent of measurement. Most physicists have concluded that both locality and realism must be abandoned in some form. The experimental tests of Bell inequalities began in earnest in the 1970s and 80s, with the pioneering work of physicists like Alain Aspect in France. These experiments involved creating pairs of entangled photons and measuring their polarizations along different axes, chosen randomly just before the measurements took place. The random choice of measurement axes was crucial because it prevented any possible communication between the measurement apparatus and the photons from influencing the results. Aspect's experiments, and many subsequent tests with ever greater precision and sophistication, have consistently confirmed the quantum mechanical predictions and violated Bell inequalities. Nature does indeed exhibit non-local correlations that cannot be explained by any theory based on local hidden variables. The instantaneous connections between entangled particles are not just theoretical curiosities, but measurable features of our universe. To understand what entanglement actually means in practice, consider a pair of photons created in a special quantum state where their total angular momentum is zero. If we measure the polarization of one photon and find it oriented vertically, quantum mechanics tells us that measuring the other photon's polarization will definitely yield a horizontal result. This correlation holds regardless of how far apart the photons have traveled, even if they are separated by millions of kilometers. The truly strange aspect is that before either measurement takes place, quantum mechanics insists that neither photon has a definite polarization. They exist in a superposition state, simultaneously vertically and horizontally polarized until the moment of measurement. The act of measuring one photon not only determines its polarization, but instantly determines the polarization of its distant partner, even though no signal can travel between them faster than light. This phenomenon extends far beyond photons to include electrons, atoms, and even larger objects. Scientists have created entangled states involving the spins of electrons separated by large distances, the energy levels of atoms in different laboratories, and even the vibrational modes of mechanical resonators visible to the naked eye. The scale and complexity of entangled systems that can be created and maintained continue to grow as experimental techniques become more sophisticated. Understanding entanglement requires grappling with the concept of quantum superposition, the idea that quantum systems can exist in combinations of different states simultaneously. An electron can be spinning both clockwise and counterclockwise at the same time, or a photon can travel through two different paths simultaneously, until a measurement forces the system to choose one definite outcome. When two or more quantum systems become entangled, their individual quantum states become undefined, while the combined state of the entire system remains perfectly well defined. We cannot say anything definite about the properties of individual particles in an entangled pair, but we can make precise predictions about the results of measurements performed on both particles together. This loss of individual identity in favor of collective quantum coherence represents one of the most fundamental departures from our classical intuitions about reality. In the everyday world, objects have definite properties whether or not anyone observes them, and knowing everything about individual components allows us to predict the behavior of the whole system. Quantum entanglement turns this logic on its head, creating situations where the whole system has definite properties, while its individual parts remain fundamentally indefinite. The mathematical description of entanglement relies on the concept of the quantum state vector, a mathematical object that encodes all possible information about a quantum system. For a single particle, this state vector might describe its position, momentum, spin, and other properties as probability distributions rather than definite values. When particles become entangled, their individual state vectors become mathematically inseparable, forming a composite state that cannot be decomposed into independent parts. This mathematical inseparability has profound physical consequences. Any attempt to measure or manipulate one particle in an entangled pair necessarily affects the quantum state of the entire system, including particles that may be arbitrarily far away. The effect is not due to any signal traveling between the particles, but rather reflects the fundamentally holistic nature of quantum reality at the deepest level. Quantum entanglement has been verified not just in carefully controlled laboratory experiments, but also in increasingly practical applications. Quantum cryptography uses entangled particles to create communication channels that are fundamentally secure, because any attempt to eavesdrop necessarily disturbs the quantum state in detectable ways. Quantum computing relies on entanglement to perform certain calculations exponentially faster than classical computers by manipulating quantum information in ways that exploit the parallel processing capabilities of superposition states. These applications have driven the development of increasingly sophisticated techniques for creating, manipulating, and measuring entangled states. Scientists can now routinely produce entangled photons using nonlinear crystals, entangled electrons using quantum dots, and entangled atoms using laser cooling and trapping techniques. The degree of control achieved over quantum systems has reached the point where large-scale quantum computers and quantum communication networks are becoming technologically feasible. Yet for all the practical applications, entanglement remains deeply mysterious from a conceptual standpoint. How can particles that have never interacted become entangled? What happens to entanglement when particles pass through regions of curved space-time? Can entanglement exist between particles separated by event horizons of black holes? These questions push the boundaries of our understanding and hint at connections between quantum mechanics and gravity that are only beginning to be explored. One of the most intriguing aspects of entanglement is its relationship to information. When two particles are maximally entangled, measuring one provides complete information about the other. But this information cannot be used to communicate faster than light. The correlations revealed by entanglement are purely quantum mechanical and cannot be used to transmit classical information between distant locations. This limitation, known as the no communication theorem, preserves the causal structure of relativity while allowing for non-local quantum correlations. It suggests that entanglement represents a form of information sharing that is fundamentally different from classical communication, operating through the quantum mechanical structure of reality rather than through the transmission of signals through space-time. The information theoretic perspective on entanglement has led to profound insights about the relationship between quantum mechanics and thermodynamics. Entanglement can be quantified using measures borrowed from information theory, such as entropy and mutual information, providing mathematical tools for understanding how quantum correlations evolve and degrade over time. When entangled particles interact with their environment through processes like collisions with other particles or absorption of thermal radiation, their entanglement gradually decreases in a process called decoherence. This environmental interference explains why entanglement is difficult to maintain in warm, noisy environments, and why quantum effects typically disappear at macroscopic scales. However, entanglement is remarkably robust under certain conditions. Entangled photons can maintain their correlations while traveling through kilometers of optical fiber, or even through the atmosphere and space. This robustness makes entanglement-based technologies practical and suggests that quantum correlations play important roles in natural systems, ranging from photosynthesis in plants to navigation in migratory birds. The study of entanglement has also revealed deep connections to other areas of physics. In condensed matter systems, entanglement helps explain exotic phases of matter, such as quantum spin liquids and topological superconductors. In high-energy physics, entanglement appears to play crucial roles in the structure of the quantum vacuum and the behavior of quantum field theories. Perhaps most remarkably, recent theoretical work suggests that entanglement might be intimately connected to the structure of space-time itself. The idea that spatial connections between distant regions might emerge from quantum entanglement represents a radical departure from traditional thinking about the relationship between matter and geometry. If this connection proves real, it could provide the key to unifying quantum mechanics and gravity in ways that neither theory can achieve alone. As experimental techniques continue to improve, scientists are pushing entanglement into new regimes that test the boundaries between quantum and classical behavior. Experiments with increasingly massive objects in quantum superposition states probe whether quantum mechanics applies universally or gives way to some other theory at large scales. These tests also explore whether gravitational interactions might play a role in the transition from quantum to classical behavior. The implications of quantum entanglement extend far beyond physics into questions about the nature of reality, consciousness, and our place in the universe. If particles can be connected across vast distances in ways that transcend the classical limitations of space and time, what does this mean for our understanding of separation, individuality, and the fundamental structure of existence itself? These questions, once relegated to philosophy, are now subjects of active scientific investigation, as our ability to create and control entangled systems reaches unprecedented levels of sophistication. In 2013, two of the most brilliant theoretical physicists of our time, Juan Maldacena of the Institute for Advanced Study and Leonard Susskind of Stanford University, proposed an idea so audacious and elegant that it has fundamentally changed how physicists think about the relationship between gravity and quantum mechanics. Their conjecture, known as ER equals EPR, suggests that Einstein-Rosen bridges, the technical name for wormholes, and Einstein-Podolsky-Rosen correlations, the technical name for quantum entanglement, are actually two different descriptions of the same underlying phenomenon. This proposal represents a stunning convergence of ideas that Einstein himself helped develop but never imagined could be connected. On one side stands the Einstein-Rosen bridge, a solution to Einstein's field equations discovered in 1935 that describes a tunnel through space-time connecting two distant regions of the universe. On the other side lies the EPR paradox, also formulated in 1935, which highlighted the mysterious non-local correlations that troubled Einstein so deeply about quantum mechanics. The ER equals EPR conjecture suggests that these two seemingly unrelated concepts are actually different perspectives on the same physical reality. When two particles become quantum entangled, they may be connected not just through abstract quantum correlations, but through actual geometric structures in space-time itself. The non-local connections that Einstein called spooky action at a distance might literally be shortcuts through the fabric of space-time. To understand this revolutionary idea, we must first examine what Einstein-Rosen bridges actually represent in the context of general relativity. A wormhole is a hypothetical tunnel that connects two separate regions of space-time through a higher dimensional shortcut. Imagine a piece of paper with 2 points marked on it. The shortest path between these points along the surface of the paper is a straight line, but if you fold the paper so that the 2 points touch, you could connect them with a much shorter path that passes through the three-dimensional space surrounding the paper. Similarly, a wormhole represents a fold in space-time that allows two distant regions to be connected through a path that is much shorter than the distance measured along the normal three-dimensional space. A wormhole connecting Earth and a star 1,000 light-years away might allow travel between these locations in just a few hours, even though the normal space-time distance requires 1,000 years to traverse at light speed. The mathematical description of wormholes emerges naturally from Einstein's field equations under certain exotic conditions. The simplest wormhole solution, discovered by Einstein and Rosen themselves, connects two identical black holes in different regions of space-time. Matter falling into one black hole could theoretically emerge from the other, having traveled through the connecting tunnel rather than being crushed at the black hole's center. However, these classical wormholes face severe stability problems. Detailed calculations show that they would collapse faster than light could travel through them, making them useless for actual travel or communication. To keep a wormhole open requires exotic matter with negative energy density, a form of matter that may not exist in nature. Even if such matter could be found or created, maintaining a traversable wormhole would require amounts of energy comparable to that contained in stellar masses. These practical difficulties led most physicists to dismiss wormholes as interesting mathematical curiosities, with no relevance to the real universe. The energy requirements seemed impossibly large, the stability problems appeared insurmountable, and there was no observational evidence for their existence. Wormholes remained popular in science fiction, but were largely ignored by serious physicists working on quantum gravity. The ER equals EPR conjecture changes this picture dramatically by suggesting that wormholes might exist not as macroscopic tunnels for space travel, but as microscopic quantum structures that create and maintain entanglement between particles. In this view, every pair of entangled particles is connected by a tiny wormhole that exists in the quantum foam of space, time at the Planck scale. This connection would explain the mysterious non-local correlations of quantum entanglement in terms of actual geometric structures. When we measure one particle in an entangled pair and instantly determine properties of its distant partner, information might be traveling through a microscopic wormhole that connects the two particles. The apparent violation of relativity's speed limit would be resolved because the information travels through a shortcut in space-time rather than across the normal three-dimensional distance. The mathematical support for this idea comes from advances in string theory and the holographic principle, particularly through the ADS-CFT correspondence. This correspondence establishes a precise mathematical relationship between certain theories of gravity in spaces with negative curvature, called anti-de Sitter spaces, and quantum field theories without gravity defined on the boundaries of those spaces. In the ADS-CFT correspondence, quantum entanglement between different regions of the boundary theory corresponds to geometric connections, including wormholes in the interior gravitational theory. This provides a concrete mathematical realization of the ER equals EPR idea, at least in the special case of these highly symmetric spacetimes. The correspondence shows that when boundary regions become more entangled, the interior spacetime develops stronger geometric connections. When entanglement decreases through decoherence or other processes, the interior geometry becomes more disconnected. This suggests a deep relationship between the connectivity of spacetime and the pattern of quantum entanglements in matter and energy. One of the most compelling applications of ER equals EPR involves black holes and the information paradox that has puzzled physicists for decades. When matter falls into a black hole, quantum mechanics insists that the information it carries cannot be destroyed, but general relativity suggests that this information disappears forever behind the event horizon. This apparent contradiction has generated thousands of research papers and numerous proposed solutions. The ER equals EPR conjecture offers a new perspective on this paradox by suggesting that information falling into a black hole becomes entangled with information that escapes in the form of Hawking radiation. This entanglement is maintained through microscopic wormholes that connect the interior and exterior of the black hole, allowing information to eventually escape while preserving the principles of both quantum mechanics and general relativity. In this picture, a black hole is not an isolated object that destroys information, but rather one end of a vast network of wormhole connections that link it to the rest of the universe. The Hawking radiation that slowly evaporates the black hole carries with it quantum correlations that preserve all the information that ever fell in. But this information is encoded in such a subtle way that it cannot be decoded without access to the interior of the black hole. This resolution of the information paradox has profound implications for our understanding of space-time and quantum mechanics. It suggests that the interior of a black hole may not be the isolated, disconnected region that general relativity seems to describe, but rather an integral part of a larger quantum mechanical system that includes the exterior universe. The ER equals EPR idea also provides new insights into the emergence of space-time from quantum mechanics. If entanglement creates geometric connections, then the structure of space-time itself might emerge from the pattern of quantum correlations in some more fundamental quantum system. Space and time would not be the fixed background against which physics takes place, but rather emergent properties of quantum information processing. This perspective suggests that the smooth space-time of general relativity is an approximation that applies when quantum systems are sufficiently entangled to create stable geometric structures. In regions where entanglement is weak or absent, space-time might become discontinuous or even cease to exist in any meaningful sense. The geometry of the universe would be determined by the quantum information content of matter and energy rather than by classical field equations. Such ideas push the boundaries of physics into territory that Einstein himself might not have recognized, despite the fact that the key concepts bear his name. The notion that space-time emerges from quantum entanglement represents a complete reversal of the traditional relationship between geometry and quantum mechanics. Instead of quantum fields evolving on a fixed space-time background, space-time itself becomes a quantum phenomenon subject to the uncertainties and correlations of quantum mechanics. However, the ER equals EPR conjecture remains highly speculative and faces significant challenges. The microscopic wormholes it postulates exist at the Planck scale, far below the reach of any conceivable experiment. The mathematical framework supporting the idea works clearly only in highly simplified situations that may not reflect the complexity of our actual universe. Most importantly, the conjecture has not yet led to specific, testable predictions that would allow experimental verification or falsification. Critics argue that the apparent connection between wormholes and entanglement might be an artifact of the special mathematical models used to study them, rather than a fundamental feature of nature. The ADS-CFT correspondence, while mathematically elegant, applies to spacetimes with negative cosmological constants, unlike our universe, which appears to have a positive cosmological constant. Whether the insights gained from these model systems apply to realistic situations remains an open question. Furthermore, the idea that information travels through wormholes to maintain entanglement correlations raises questions about causality and the foundations of relativity. Even if wormholes provide shortcuts through spacetime, the requirement that entanglement correlations be maintained instantaneously seems to demand faster than light information transfer, potentially violating the causal structure that relativity works so hard to preserve. Proponents of ER equals EPR argue that these apparent violations of causality are resolved by the quantum mechanical nature of the information transfer. The correlations maintained through wormholes are purely quantum mechanical and cannot be used to send classical information faster than light, preserving the no communication theorem that prevents entanglement from violating relativity. The wormholes facilitate quantum correlation rather than classical communication. Despite these challenges and uncertainties, the ER equals EPR conjecture has energized research at the interface between gravity and quantum mechanics. It provides a concrete mathematical framework for exploring how spacetime and quantum entanglement might be related, even if the ultimate truth of the relationship remains to be determined. The idea has already led to new insights about black holes, quantum error correction, and the emergence of space-time from quantum mechanics. The conjecture also suggests experimental programs that might test its implications. If entanglement creates geometric connections, then manipulating entanglement in laboratory systems might produce detectable gravitational effects. Conversely, gravitational phenomena might be used to create or manipulate entanglement in ways that pure quantum mechanical methods cannot achieve. Perhaps most importantly, ER equals EPR represents a conceptual breakthrough in how physicists think about the relationship between different areas of physics. By connecting seemingly disparate phenomena through elegant mathematical relationships, it exemplifies the kind of deep unification that physicists hope will eventually lead to a complete theory of quantum gravity. As we stand at the threshold of potentially revolutionary discoveries about the nature of space, time, and quantum mechanics, the ER equals EPR conjecture serves as both an inspiration and a challenge. It shows how ideas that Einstein developed in the 1930s working in isolation on apparently unrelated problems, might be connected in ways that could transform our understanding of reality itself. Whether this connection proves to be a fundamental truth about nature or an elegant mathematical coincidence remains one of the most important open questions in contemporary physics. While theoretical physicists debate whether wormholes and entanglement represent different faces of the same phenomenon, experimental physicists are asking a more direct question: can gravity itself create quantum entanglement? This seemingly simple question opens the door to some of the most ambitious and technically challenging experiments ever conceived, pushing the boundaries of both quantum control and gravitational measurement into uncharted territory. The idea that gravity might induce entanglement between previously uncorrelated quantum systems represents a potential bridge between the macroscopic world of general relativity and the microscopic realm of quantum mechanics. If successful, such experiments would provide the first direct evidence that gravity operates according to quantum mechanical principles, potentially revolutionizing our understanding of both phenomena. The theoretical foundation for gravitationally induced entanglement was laid in the early 2000s by physicists including Chiara Marletto and Vlatko Vedral at Oxford University, along with Sugato Bose at University College London. Their proposal, now known as the Bose-Marletto-Vedral or BMV protocol, suggests that two masses placed in quantum superposition states can become entangled through their mutual gravitational interaction, even if they never interact through any other force. The basic idea behind the BMV proposal is elegantly simple in principle, but extraordinarily difficult to implement in practice. Imagine two small masses, each roughly the size of a grain of sand, but containing billions of atoms. Using techniques borrowed from quantum optics and atomic physics, these masses are placed in quantum superposition states, where each mass exists in two slightly different positions simultaneously. When a mass is in such a superposition state, its gravitational field is also in superposition, creating a quantum gravitational field that can influence other quantum systems. If two masses in superposition are brought close enough together that their gravitational fields overlap, quantum mechanics predicts that they should become entangled through purely gravitational interactions. The entanglement arises because the gravitational force between the masses depends on their relative positions. When both masses are in superposition states, the strength of their gravitational interaction becomes quantum mechanically uncertain, correlating the quantum states of the two masses in a way that creates entanglement. Measuring the position of one mass would then instantly determine correlations in the quantum state of the other mass, regardless of how far apart they had been moved. This gravitational entanglement would be fundamentally different from entanglement created through electromagnetic, weak, or strong nuclear interactions. It would demonstrate that gravity, like the other fundamental forces, operates according to quantum mechanical principles rather than purely classical laws. More importantly, it would provide direct experimental evidence that space-time itself has quantum properties, since gravitational fields are manifestations of space-time curvature. The experimental challenges involved in detecting gravitationally induced entanglement are staggering. Gravity is by far the weakest of the fundamental forces, weaker than electromagnetism by a factor of about 10 to the 36th power. This means that gravitational effects on quantum systems are typically overwhelmed by electromagnetic and other interactions by enormous margins. To isolate gravitational effects, experimenters must create conditions where all other forces are either eliminated or precisely controlled. The masses must be electrically neutral to avoid electromagnetic interactions, magnetically shielded to prevent magnetic forces, and isolated from vibrations and other environmental disturbances that could mask or mimic gravitational effects. Even tiny electric charges, equivalent to just a few elementary charges on masses containing billions of atoms, would create electromagnetic forces millions of times stronger than the gravitational forces being measured. The quantum control requirements are equally demanding. The masses must be cooled to temperatures close to absolute zero to minimize thermal motion that would destroy quantum coherence. They must be isolated from environmental decoherence sources such as gas molecules, thermal radiation, and electromagnetic fields. Most challenging of all, they must be placed in quantum superposition states while remaining massive enough that their gravitational fields can influence each other. Current quantum control techniques can routinely create superposition states of individual atoms, small molecules, and even clusters of thousands of atoms. However, scaling these techniques to objects massive enough to produce detectable gravitational effects requires revolutionary advances in quantum technology. The masses must be heavy enough that their gravitational influence is measurable, but light enough that quantum superposition states can be created and maintained. Several experimental groups around the world are pursuing different approaches to this challenge. Some focus on levitated nanoparticles, tiny spheres of dense materials like gold or diamond that can be trapped and cooled using optical or electromagnetic fields. These particles can contain millions or billions of atoms while remaining small enough that advanced quantum control techniques might be applied to them. Other groups are investigating mechanical resonators, microscopic structures that vibrate like tiny bells or drums. These resonators can be cooled to their quantum mechanical ground states and placed in superposition states of different vibrational modes. If two such resonators are designed to interact gravitationally, they might become entangled through the quantum mechanical nature of their gravitational interaction. The most ambitious proposals involve creating superposition states of objects visible to the naked eye, containing perhaps 10 to the 15th power atoms or more. Such experiments would push quantum mechanics into regimes never before explored, testing whether quantum principles apply universally or give way to some other theory at macroscopic scales. One promising approach uses optical techniques to trap and cool tiny mirrors or mechanical cantilevers to their quantum ground states. These objects can then be placed in superposition states of different positions or vibrational modes using carefully controlled laser pulses. If two such objects are positioned appropriately, their gravitational interaction might create detectable entanglement. The detection of gravitational entanglement requires measurement techniques sensitive enough to distinguish quantum correlations from classical correlations that might arise through other mechanisms. This typically involves performing many repeated measurements on identically prepared systems and analyzing the statistical correlations between measurement outcomes on different masses. The analysis must account for all possible sources of classical correlation, including residual electromagnetic interactions, mechanical vibrations transmitted through mounting structures, and correlated environmental effects, such as temperature fluctuations or electromagnetic interference. Only correlations that violate Bell inequalities or exhibit other uniquely quantum signatures can be considered evidence of genuine quantum entanglement. Several groups have reported progress toward implementing gravitational entanglement experiments, though none has yet achieved the full goal of detecting entanglement created purely through gravitational interactions. The technical challenges remain formidable, requiring advances in quantum control, vibration isolation, electromagnetic shielding, and measurement sensitivity that push multiple technologies to their fundamental limits simultaneously. One intermediate goal involves detecting gravitational effects on quantum systems without necessarily creating entanglement. Experiments have been proposed to measure how gravitational fields affect the quantum states of individual particles, atoms, or small objects. Such measurements would still provide evidence for the quantum nature of gravity, even if they fall short of demonstrating gravitational entanglement. Another approach focuses on using gravity to mediate interactions between quantum systems that are otherwise completely isolated from each other. If two quantum systems can only interact through gravity, any correlations between them must arise through gravitational mechanisms, This approach might be easier to implement than creating full entanglement, while still providing valuable information about quantum gravitational effects. The implications of successfully detecting gravitationally induced entanglement would extend far beyond confirming theoretical predictions. Such experiments would open entirely new avenues for studying quantum gravity, providing laboratory access to phenomena that previously could only be studied through astronomical observations or theoretical calculations. Gravitational entanglement might also enable new forms of quantum technology. If gravity can create and manipulate entanglement, it might be possible to use gravitational fields as tools for quantum information processing, quantum communication, or quantum sensing. The weakness of gravity, usually seen as a disadvantage, might become an asset for delicate quantum manipulations that stronger forces would disrupt. Perhaps most intriguingly, gravitational entanglement experiments might provide insights into the fundamental structure of spacetime itself. If spacetime emerges from quantum entanglement, as suggested by the ER, equals EPR conjecture, then creating gravitational entanglement in the laboratory might literally involve manipulating the geometry of spacetime on microscopic scales. The experimental search for gravitational entanglement also connects to broader questions about the boundary between quantum and classical physics. The masses involved in these experiments occupy a middle ground between the microscopic quantum world and the macroscopic classical world. Understanding how gravity affects quantum systems in this intermediate regime might reveal new physics that bridges the gap between quantum mechanics and general relativity. Current experiments are still in their early stages, with most groups focusing on developing the necessary technologies and techniques rather than attempting complete implementations of gravitational entanglement protocols. The required advances in quantum control, isolation techniques, and measurement sensitivity are substantial, likely requiring years or decades of development before definitive results become available. Nevertheless, the potential rewards justify the enormous technical challenges involved. Gravitational entanglement experiments represent humanity's best hope for directly testing the quantum nature of gravity in laboratory settings, providing experimental access to phenomena that might otherwise remain forever beyond our reach. As experimental techniques continue to advance and theoretical understanding deepens, the prospect of detecting gravitationally induced entanglement becomes increasingly realistic. Success would mark a watershed moment in physics, providing the first direct evidence that gravity operates according to quantum principles, and opening new chapters in our understanding of space, time, and the fundamental structure of reality itself. While laboratory experiments struggle to detect gravity's influence on quantum entanglement, nature provides laboratories where gravitational effects are so extreme that quantum mechanics and general relativity collide with spectacular consequences. Black holes, neutron stars, and the moments following the Big Bang represent cosmic arenas where the marriage between gravity and quantum mechanics is not just theoretical speculation, but a necessity for understanding some of the most profound phenomena in the universe. Black holes stand as the ultimate testing grounds for theories that attempt to unify gravity with quantum mechanics. These cosmic monsters, where matter has collapsed to such extreme density that space-time curves back on itself, create conditions where both gravitational and quantum effects become equally important. The event horizon, that mysterious boundary beyond which nothing can escape, marks the frontier where our understanding of physics transitions from confidence to confusion. The story of quantum mechanics in extreme gravity begins with Stephen Hawking's revolutionary discovery in 1974 that black holes are not perfectly black, but actually emit radiation through quantum mechanical processes near their event horizons. This Hawking radiation emerges from quantum fluctuations in the vacuum of space-time, where virtual particle pairs are constantly appearing and disappearing throughout the universe. Near a black hole's event horizon, these quantum fluctuations take on special significance. When a virtual particle pair appears just outside the horizon, one particle may fall into the black hole while the other escapes to infinity. The escaping particle becomes real Hawking radiation, carrying away energy and causing the black hole to slowly evaporate. This process represents a fundamental connection between gravity, quantum mechanics, and thermodynamics that has profound implications for our understanding of all three subjects. The temperature of Hawking radiation depends inversely on the black hole's mass, meaning that smaller black holes are hotter than larger ones. For a black hole with the mass of our Sun, the Hawking temperature is approximately 10 to the -7 power Kelvin, far colder than the cosmic microwave background radiation. Such black holes actually absorb more energy from their surroundings than they emit, causing them to grow rather than evaporate. However, primordial black holes created in the early universe could have much smaller masses and correspondingly higher temperatures. A black hole with the mass of a mountain would have a temperature of billions of degrees and would evaporate completely in a fraction of a second, releasing energy equivalent to millions of hydrogen bombs. If such black holes exist, they would represent natural laboratories where quantum gravity effects could be observed directly. The evaporation of black holes through Hawking radiation creates one of the most perplexing puzzles in theoretical physics, known as the black hole information paradox. When matter falls into a black hole, it carries with it quantum information about its properties, composition, and quantum state. Classical general relativity suggests that this information disappears forever when the matter crosses the event horizon and is crushed at the black hole's center. Quantum mechanics, however, insists that information cannot be destroyed. The fundamental principles of quantum theory require that the quantum state of any system evolve in a completely reversible way, meaning that information about initial conditions must always be preserved, even if it becomes practically inaccessible. This principle, known as unitarity, is one of the bedrock assumptions of quantum mechanics and has never been observed to fail in any experiment. The information paradox becomes acute when black holes evaporate completely through Hawking radiation. If the information that fell into the black hole has been destroyed, then the final state of the universe after evaporation contains less information than the initial state, violating unitarity. But if the information somehow escapes in the Hawking radiation, it must emerge in a highly scrambled form that preserves quantum correlations with matter that fell in potentially billions of years earlier. Various proposals have been advanced to resolve this paradox, each with profound implications for our understanding of space-time and quantum mechanics. Some suggest that information is gradually leaked out in the Hawking radiation through subtle quantum correlations that become apparent only when the black hole has evaporated significantly. Others propose that the information is released in a sudden burst when the black hole reaches a critical size, or that it never actually crosses the event horizon in the first place due to subtle quantum effects. The role of quantum entanglement in resolving the information paradox has become increasingly central to current research. When matter falls into a black hole, it may become entangled with the Hawking radiation being emitted from the black hole's surface. This entanglement could preserve the information content of the infalling matter while making it accessible only through measurements that combine observations of both the black hole interior and the external Hawking radiation. This entanglement-based resolution suggests that black holes are not isolated objects that destroy information, but rather components of larger quantum systems that include both the black hole interior and all the Hawking radiation it has ever emitted. The information about infalling matter is preserved through quantum correlations that span the event horizon, connecting the interior and exterior regions in ways that classical general relativity cannot describe. The practical implications of this picture are staggering. It suggests that anyone who falls into a black hole remains quantum mechanically connected to observers outside the black hole through entanglement mediated by Hawking radiation. The information about the falling observer's quantum state is gradually transferred to the external universe through these quantum correlations, even though the observer themselves can never return. This resolution of the information paradox has led to the firewall controversy, one of the most heated debates in contemporary theoretical physics. Some physicists argue that preserving quantum mechanical unitarity requires the event horizon to be replaced by a wall of high-energy radiation that would instantly incinerate anything attempting to cross it. This firewall would preserve information by preventing matter from ever actually entering the black hole interior. Others maintain that the equivalence principle, Einstein's fundamental insight that gravity is indistinguishable from acceleration, requires that freely falling observers experience nothing unusual when crossing the event horizon. According to this view, the event horizon should be a smooth, empty region of space-time where infalling observers can pass through unharmed, at least until they approach the black hole's center. The firewall debate highlights the tension between different principles of physics when pushed to their limits. Preserving quantum unitarity seems to require firewalls, but maintaining general covariance and the equivalence principle seems to require smooth horizons. Resolving this tension may require modifications to our understanding of either quantum mechanics or general relativity, or both. Recent developments in the study of black hole entanglement have focused on the concept of quantum error correction and its relationship to the emergence of space-time geometry. Just as quantum error correction allows quantum computers to preserve quantum information despite environmental noise, the entanglement structure of black holes might naturally implement error correction mechanisms that preserve information while allowing space-time geometry to emerge from quantum correlations. In this picture, the interior of a black hole is not a separate region of space-time, but rather an emergent description that arises from quantum entanglement between different parts of the black hole system. The geometry of the black hole interior is encoded in the pattern of entanglement between Hawking radiation quanta, with spatial relationships emerging from the structure of quantum correlations. This connection between entanglement and geometry extends beyond black holes to other extreme gravitational environments. Neutron stars, with densities exceeding that of atomic nuclei and magnetic fields, trillions of times stronger than Earth's, create conditions where quantum effects influence macroscopic phenomena in observable ways. The matter inside neutron stars exists in exotic quantum states that have no terrestrial analogues, potentially exhibiting superfluidity, superconductivity, and other quantum phases under extreme gravitational pressure. The quantum properties of neutron star matter may be observable through gravitational wave signals produced when neutron stars merge. The detailed waveforms of these signals encode information about the equation of state of nuclear matter at densities and pressures that cannot be reproduced in terrestrial laboratories. As gravitational wave detectors become more sensitive, they may reveal quantum mechanical properties of matter in gravitational environments billions of times more extreme than anything on Earth. The early universe provides another natural laboratory for studying quantum mechanics in extreme gravitational fields. During cosmic inflation, quantum fluctuations in hypothetical fields called inflatons were stretched to astronomical scales, seeding the density variations that eventually grew into galaxies and galaxy clusters. The cosmic microwave background radiation carries imprints of these primordial quantum fluctuations, providing observational access to quantum mechanics, operating under conditions of extreme space-time curvature. Future observations of gravitational waves from the early universe could provide even more direct information about quantum gravity effects. Primordial gravitational waves, if they exist, would carry information about the quantum state of space-time itself during the first moments after the Big Bang. Detecting these waves would provide the first direct observational evidence for the quantum mechanical nature of gravity under the most extreme conditions imaginable. The study of entanglement in extreme gravity has also revealed unexpected connections to quantum information science and the foundations of quantum mechanics. Black holes turn out to be remarkably efficient scramblers of quantum information, mixing infalling information so thoroughly that it becomes practically impossible to recover without access to the complete Hawking radiation. This scrambling process provides insights into how quantum information spreads and thermalizes in strongly interacting quantum systems. The holographic principle, which emerged from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on its boundary surface. This principle has led to revolutionary insights in both gravity and quantum field theory, revealing deep connections between entanglement, quantum error correction, and the emergence of space-time geometry. These developments have practical implications for quantum technology, as well as fundamental physics. Understanding how quantum information behaves in curved space-time could inform the design of quantum computers and quantum communication systems. The natural quantum error correction mechanisms discovered in black hole physics might inspire new approaches to protecting quantum information from environmental decoherence. As our observational capabilities continue to improve, we are entering an era when the quantum properties of extreme gravitational systems may become directly observable. The recent detection of gravitational waves from merging black holes and neutron stars has opened an entirely new window into the universe, potentially providing access to quantum gravitational phenomena that were previously beyond experimental reach. The next generation of gravitational wave detectors, space-based interferometers, and high-energy particle experiments may reveal quantum signatures in astrophysical systems that operate under conditions where both gravity and quantum mechanics are equally important. These observations could provide the first direct tests of quantum gravity theories and reveal how entanglement behaves in the most extreme environments nature can provide. The implications extend far beyond academic physics. Understanding quantum mechanics in extreme gravity could reveal new principles of quantum information processing, provide insights into the nature of space-time itself, and possibly point toward technologies that harness quantum gravitational effects for practical purposes. The cosmic laboratories provided by black holes, neutron stars, and the early universe may hold keys to unlocking the deepest secrets of quantum gravity and the fundamental structure of reality itself. The quest to understand how gravity and quantum entanglement might be connected has led physicists to propose several radically different approaches to quantum gravity, each offering its own perspective on how space-time and quantum mechanics might be unified. These theoretical frameworks represent some of the most ambitious intellectual undertakings in the history of science, attempting to reconcile two of our most successful but seemingly incompatible descriptions of nature. Loop quantum gravity stands as one of the most direct attempts to quantize Einstein's theory of general relativity, using the mathematical techniques that proved so successful for the other fundamental forces. Developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, beginning in the 1980s, this approach treats space-time itself as a quantum mechanical system, with discrete, granular structure at the smallest scales. In loop quantum gravity, space is not the smooth continuum that classical general relativity assumes, but rather a network of discrete geometric building blocks connected by quantum mechanical links. At the Planck scale, approximately 10 to the minus 35 power meters, space-time resembles a fabric woven from fundamental loops and nodes, each carrying precise amounts of area and volume in units determined by the fundamental constants of nature. This discrete structure of space emerges from the mathematical requirement that certain geometric quantities, such as areas and volumes, must be quantized in any consistent quantum theory of gravity. Just as the energy levels of atoms are quantized in quantum mechanics, the geometric properties of space-time are quantized in loop quantum gravity, leading to a universe where space itself has an atomic structure. The implications for entanglement in loop quantum gravity are profound but still being explored. If space-time consists of discrete quantum degrees of freedom, then entanglement between these fundamental geometric units might play a crucial role in determining the large-scale structure of space-time. The connectivity of the loop network could emerge from entanglement patterns between neighboring nodes, with strongly entangled regions corresponding to smooth, continuous space-time, and weakly entangled regions corresponding to discontinuous or highly curved geometries. One of the most striking predictions of loop quantum gravity is the resolution of classical singularities through quantum effects. In classical general relativity, the centers of black holes and the initial moment of the Big Bang represent singularities where densities and curvatures become infinite and the laws of physics break down. Loop quantum gravity suggests that these singularities are replaced by quantum bounces, where matter reaches maximum density and then rebounds, avoiding infinite compression. This quantum bounce mechanism could have dramatic implications for black hole physics and cosmology. Instead of crushing matter to infinite density, black holes might internally rebound and eventually emit their contents back into the external universe. The Big Bang might be preceded by a previous contracting phase of the universe, with quantum gravitational effects causing a bounce that initiates the expansion we observe today. String theory takes a completely different approach to quantum gravity by proposing that the fundamental constituents of nature are not point-like particles, but tiny vibrating strings existing in 10 or 11 dimensions. Developed originally as a theory of the strong nuclear force in the 1970s, string theory evolved into a candidate theory of everything when physicists realized that it naturally incorporates gravity as one of the vibrational modes of the fundamental strings. In string theory, gravity emerges from the vibrations of closed strings, loops that can oscillate in various patterns corresponding to different particles and forces. The graviton, the hypothetical quantum particle that mediates gravitational interactions, appears naturally as one of these vibrational modes, providing a quantum mechanical description of gravity that avoids many of the technical difficulties encountered in other approaches. The extra dimensions required by string theory are typically assumed to be compactified or curled up at scales too small to observe directly. The precise way these extra dimensions are compactified determines the properties of particles and forces that we observe in our four-dimensional world. This flexibility allows string theory to potentially explain why our universe has exactly the particles and forces that we observe, but it also leads to an enormous number of possible string theory vacua, each corresponding to different possible universes. Entanglement plays several important roles in string theory approaches to quantum gravity. The fundamental strings themselves can become entangled, creating correlations between different vibrational modes that persist even when the strings separate to large distances. These entangled string states might provide the microscopic foundation for the macroscopic entanglement phenomena observed in quantum field theory and condensed matter physics. More remarkably, string theory has revealed deep connections between entanglement and the emergence of space-time geometry through the ADS-CFT correspondence. This duality, discovered by Juan Maldacena in 1997, establishes a precise mathematical relationship between certain string theories in curved spacetimes and quantum field theories without gravity, defined on the boundaries of those spacetimes. In the ADS-CFT correspondence, quantum entanglement in the boundary theory corresponds directly to geometric connections in the interior gravitational theory. When regions of the boundary become more entangled, the interior spacetime develops stronger geometric connectivity, potentially including wormhole-like structures that provide shortcuts between distant boundary regions. This provides a concrete realization of the ER equals EPR conjecture within the framework of string theory. The holographic principle that emerges from ADS-CFT suggests that gravity might be fundamentally holographic, with all the information in a volume of space encoded on its boundary surface. This principle has revolutionized our understanding of quantum gravity by suggesting that spacetime itself might be an emergent phenomenon arising from quantum entanglement in lower dimensional theories. However, String theory faces significant challenges in making contact with observable physics. The theory requires extra dimensions that have never been detected, predicts particles and forces that have not been observed, and operates at energy scales far beyond the reach of any conceivable experiment. The enormous number of possible string theory vacua makes it difficult to extract unique predictions that can be tested against observations. A third major approach to quantum gravity focuses on the holographic principle and its implications for the relationship between entanglement and space-time geometry. This approach, pioneered by physicists including Leonard Susskind, Juan Maldacena, and Raphael Bousso, suggests that quantum entanglement might be the fundamental ingredient from which space-time itself emerges. In holographic theories, space-time is not a fundamental aspect of nature, but rather an emergent description that arises from quantum entanglement in more fundamental degrees of freedom. The geometry of space-time, including distances, angles, and curvature, emerges from the pattern of entanglement between these underlying quantum systems. Regions that are strongly entangled correspond to nearby points in the emergent space-time, while weakly entangled regions correspond to distant or disconnected regions. This perspective suggests that Einstein's field equations, which describe how matter curves space-time, might emerge from the dynamics of quantum entanglement rather than being fundamental laws of nature. Gravity would not be a force or a curvature of pre-existing space-time, but rather a manifestation of how entanglement patterns evolve and redistribute in response to the presence of matter and energy. The holographic approach has led to remarkable insights about black hole physics, quantum error correction, and the nature of quantum information in gravitational systems. It suggests that black holes are holographic systems where all the information about their interiors is encoded on their surfaces through quantum entanglement patterns in the Hawking radiation. Causal set theory offers yet another perspective on quantum gravity by proposing that space-time has a discrete, atomic structure based on causal relationships rather than geometric properties. In this approach, developed by Raphael Sorkin and others, the fundamental building blocks of space-time are discrete events connected by causal relationships that determine which events can influence others. The causal set approach suggests that space-time emerges from the statistical properties of large collections of causally related events, similar to how the smooth flow of a fluid emerges from the statistical behavior of its molecular components. Quantum mechanics enters through the fundamental randomness in how these causal relationships are established and evolve over time. Entanglement in causal set theory might arise from correlations between causally connected events, with strongly correlated events corresponding to nearby points in the emergent space-time. This approach provides a natural explanation for the discrete, probabilistic nature of quantum mechanics, while suggesting that space-time itself emerges from more fundamental causal structures. Asymptotic safety represents a more conservative approach to quantum gravity that attempts to construct a quantum field theory of gravity using techniques similar to those employed for the other fundamental forces. This approach, advocated by Steven Weinberg and others, suggests that gravity might have a non-trivial fixed point under the renormalization group, allowing for a consistent quantum theory without requiring modifications to the basic structure of quantum field theory. In asymptotic safety, space-time remains fundamentally continuous, but quantum fluctuations at the Planck scale modify the effective strength of gravitational interactions in ways that prevent the theory from breaking down at high energies. This approach preserves many of the familiar features of quantum field theory, while potentially resolving the technical difficulties that plague other attempts to quantize gravity. Each of these approaches to quantum gravity offers different perspectives on how entanglement might be incorporated into a fundamental theory of space-time. Loop quantum gravity suggests that entanglement between discrete geometric degrees of freedom determines the connectivity of space-time. String theory proposes that entangled string states give rise to the particles and forces we observe, with space-time emerging from the dynamics of these entangled systems. Holographic theories go furthest in making entanglement fundamental, suggesting that space-time itself emerges from entanglement patterns in lower-dimensional quantum systems. Causal set theory proposes that entanglement arises from correlations between causally connected events in discrete space-time. Asymptotic safety maintains a more traditional view where entanglement operates within a continuous but quantum-modified space-time. Despite their differences, all these approaches share the recognition that quantum entanglement must play a crucial role in any complete theory of quantum gravity. The non-local correlations that characterize entangled quantum systems provide natural mechanisms for connecting distant regions of space-time in ways that purely classical theories cannot achieve. The challenge for all approaches is to make contact with observable phenomena that can distinguish between different theoretical possibilities. Current observational constraints on quantum gravity come primarily from cosmology, black hole physics, and high-energy particle experiments. But these constraints are still too weak to definitively favor one approach over others. Future observations of gravitational waves, cosmic microwave background radiation, and high-energy particle interactions may provide more stringent tests of quantum gravity theories. The detection of primordial gravitational waves could reveal quantum fluctuations of space-time itself during cosmic inflation. Precision measurements of black hole properties through gravitational wave astronomy could test predictions about quantum black hole evaporation and information preservation. Perhaps most importantly, laboratory experiments that detect gravitationally induced entanglement or other quantum gravitational effects could provide direct tests of quantum gravity theories under controlled conditions. Such experiments would represent the first direct laboratory tests of quantum gravity, potentially resolving theoretical debates that have persisted for decades. The diversity of approaches to quantum gravity reflects both the depth of the challenges involved and the richness of possibilities for how quantum mechanics and gravity might ultimately be unified. Each approach offers valuable insights, and the final theory may incorporate elements from multiple frameworks. What seems certain is that quantum entanglement will play a central role in whatever theory eventually emerges, whether as a fundamental building block of space-time or as a crucial feature that any successful theory must explain and reproduce. If the connection between gravity and quantum entanglement proves real, it opens tantalizing possibilities for technologies that could reshape human civilization. The prospect of harnessing gravitational entanglement for practical purposes represents one of the most speculative yet potentially revolutionary frontiers in physics, where the boundary between science and science fiction becomes deliciously blurred by the strange realities of quantum mechanics and curved spacetime. The most immediate applications might emerge from using gravity as a tool for quantum information processing. Unlike electromagnetic forces, which can easily overwhelm delicate quantum states, gravity couples very weakly to matter, making it potentially ideal for manipulating quantum systems without destroying their coherence. If gravitational fields can create and control entanglement, they might enable quantum operations that are impossible with conventional techniques. Imagine quantum computers that use carefully shaped gravitational fields to entangle qubits across arbitrary distances without any physical connections between them. Such gravitational quantum processors could potentially scale to enormous sizes while maintaining quantum coherence, overcoming one of the fundamental challenges facing current quantum computing technologies. The ability to create entanglement between physically separated quantum systems using only gravitational interactions could enable distributed quantum computing networks spanning continents or even planets. The weakness of gravity, usually seen as an obstacle to detecting quantum gravitational effects, might become an advantage for quantum information applications. Because gravitational interactions are so gentle, they might preserve quantum coherence in situations where electromagnetic or other interactions would cause decoherence. This could lead to quantum memory systems with unprecedented storage times, or quantum sensors with sensitivity approaching fundamental quantum limits. More speculatively, if the ER equals EPR conjecture proves correct, and entanglement is literally mediated by microscopic wormholes, it might eventually become possible to engineer macroscopic wormholes for communication or transportation. The energy requirements for creating traversable wormholes remain staggering, requiring exotic matter with negative energy density in quantities that may be impossible to produce or control. However, the history of physics is filled with phenomena that seemed impossible until the right technological breakthroughs made them practical. Quantum communication represents another potential application where gravitational entanglement could provide unique advantages. Current quantum communication systems are limited by the distance over which entanglement can be maintained in the presence of environmental decoherence. If gravitational entanglement can operate across cosmological distances, as suggested by some interpretations of black hole physics, it might enable quantum communication networks that span the solar system or even reach nearby stars. Such gravitational quantum communication systems could be inherently secure because intercepting the communication would require manipulating gravitational fields, something far beyond current technological capabilities. The fundamental connection between entanglement and space-time geometry might make gravitational quantum communication impossible to hack without literally altering the structure of space-time itself. The precision required to detect gravitational effects on quantum systems also suggests applications in metrology and sensing. Gravitational quantum sensors might achieve unprecedented sensitivity to mass distributions, gravitational waves, or changes in space-time curvature. Such sensors could revolutionize everything from geology and mineral exploration to tests of fundamental physics and searches for dark matter. If space-time itself emerges from quantum entanglement patterns, as suggested by holographic theories of quantum gravity, it might eventually become possible to engineer space-time geometry by manipulating entanglement in controlled ways. This could lead to technologies for creating regions of altered space-time with modified gravitational properties, potentially enabling artificial gravity generation, gravitational shielding, or even localized modifications to the flow of time. The prospect of engineering space-time geometry opens possibilities that stretch the imagination. Spacecraft equipped with space-time modification systems might achieve apparent faster than light travel by contracting space in front of them and expanding space behind them, similar to the theoretical Alcubierre drive proposed by physicist Miguel Alcubierre in 1994. Such drives would not violate relativity because they would manipulate space-time itself rather than accelerating matter through space. More modestly, precise control over gravitational fields could enable revolutionary propulsion systems that manipulate space-time curvature to generate thrust without expelling reaction mass. Such propellantless drives could enable interstellar missions with spacecraft that accelerate continuously throughout their journeys, reaching significant fractions of light speed without carrying the enormous fuel loads required by conventional rockets. The potential for manipulating time itself through gravitational entanglement raises even more exotic possibilities. Einstein's theory of relativity shows that time flows differently in different gravitational fields, with time passing more slowly in stronger gravitational environments. If gravitational fields can be controlled and shaped using quantum techniques, it might become possible to create localized regions where time flows at different rates. Such temporal manipulation could have profound implications for information processing, aging, and even fundamental research. Computer systems operating in regions of accelerated time could perform calculations faster than would otherwise be possible. Biological systems could potentially be slowed down or sped up by placing them in appropriate gravitational environments. Scientific experiments requiring long observation times could be conducted in regions where time flows more quickly relative to the outside world. However, these speculative applications face enormous theoretical and practical challenges. The energy requirements for significantly manipulating space-time geometry are typically astronomical, often exceeding the total energy output of stars. The exotic matter required for many proposed space-time engineering schemes may not exist in nature and might be impossible to create artificially. Even more fundamentally, many proposed applications may be ruled out by basic principles of physics that we do not yet fully understand. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics conspire to prevent the creation of closed time-like curves that could lead to paradoxes. Similar protection mechanisms might prevent other forms of space-time engineering that could violate causality or energy conservation. The no-cloning theorem in quantum mechanics prohibits the perfect copying of arbitrary quantum states, which could limit the utility of quantum gravitational technologies for information processing. The holographic bound suggests fundamental limits on the amount of information that can be stored in any region of space, potentially constraining the capabilities of space-time-based information systems. Nevertheless, even modest applications of gravitational entanglement could have transformative effects on technology and society. Quantum sensors enhanced by gravitational effects could enable new forms of medical imaging, materials characterization, and environmental monitoring. Gravitational quantum computers could solve optimization problems that are intractable for classical computers, potentially revolutionizing logistics, drug discovery, and artificial intelligence. The development of gravitational quantum technologies would likely proceed gradually, beginning with sensitive laboratory demonstrations of gravitational effects on quantum systems and slowly scaling up to more complex and practical applications. Early applications might focus on fundamental research and precision metrology rather than large-scale engineering projects. The scientific benefits of developing gravitational quantum technologies extend far beyond their immediate applications. The process of learning to control and manipulate gravitational effects on quantum systems would deepen our understanding of both quantum mechanics and gravity, potentially leading to breakthrough discoveries about the fundamental nature of space-time and matter. Such technologies could also provide new tools for testing theories of quantum gravity and exploring the foundations of physics. Laboratory systems that can create and control gravitational entanglement would serve as test beds for theoretical predictions, allowing direct experimental investigation of phenomena that currently exist only in mathematical models. The international implications of gravitational quantum technologies could be profound. Nations that master these technologies first might gain significant advantages in computing, communication, transportation, and defense applications. The potential for space-time engineering could fundamentally alter the balance of power in space exploration and development, with implications for everything from asteroid mining to interstellar colonization. The timeline for developing practical gravitational quantum technologies remains highly uncertain. Current experiments are still struggling to detect basic gravitational effects on quantum systems, and the technological challenges involved in scaling up to practical applications are immense. Pessimistic estimates suggest that useful applications could be centuries away, while optimistic projections place them within decades if key breakthroughs occur in quantum control and gravitational manipulation. The economic implications could be revolutionary if gravitational quantum technologies prove feasible. Industries ranging from computing and communication to transportation and energy could be completely transformed. The ability to manipulate space-time itself would represent a technological capability unlike anything in human history, potentially enabling forms of engineering and manufacturing that are currently impossible to imagine. As we stand at the threshold of potentially discovering fundamental connections between gravity and quantum entanglement, we must prepare for the possibility that these connections could eventually be harnessed for practical purposes. While many proposed applications remain highly speculative, the history of physics suggests that phenomena that seem purely academic often find unexpected practical applications as our understanding and technological capabilities advance. The quest to harness gravitational entanglement represents humanity's boldest attempt to control the fundamental forces that shape reality itself. Success could usher in an era of technological capabilities that transform our species from planetary inhabitants to masters of space and time, wielding the power to engineer the very fabric of existence according to our needs and desires. If gravity and quantum entanglement are truly connected at the deepest level of reality, the implications extend far beyond new technologies or even new physics. Such a discovery would fundamentally transform our understanding of existence itself, revealing that the universe operates according to principles so strange and beautiful that they challenge our most basic assumptions about space, time, matter, and consciousness. The most profound implication concerns the nature of space and time themselves. For over 3 centuries, since Newton first formulated his laws of motion, space and time have been viewed as the fixed stage upon which the drama of physics unfolds. Even Einstein's revolutionary insights, which showed that space and time are dynamic and can be curved by matter and energy, maintained the assumption that space-time forms the fundamental arena within which all physical processes occur. If space-time emerges from quantum entanglement, this entire conceptual framework must be abandoned. Space and time would no longer be fundamental aspects of reality, but rather emergent properties that arise from more basic quantum information processes. Distance would not be a primary feature of the universe, but a derived quantity that emerges from the strength of quantum correlations between different parts of a more fundamental quantum system. This emergence of space-time from entanglement suggests that the universe is far more interconnected than classical physics ever imagined. Every point in space would be fundamentally connected to every other point through the quantum information network from which space-time emerges. The apparent separateness of distant objects would be an illusion created by weak entanglement, while strongly entangled regions would correspond to nearby locations in the emergent space-time. The implications for our understanding of causality are equally profound. In classical physics, and even in standard relativity, causality is protected by the speed of light limit, which prevents effects from preceding their causes. If quantum entanglement creates instantaneous correlations across arbitrary distances, and if these correlations are mediated by actual geometric connections through space-time, then the foundations of causal ordering require complete reconceptualization. However, the no-communication theorem in quantum mechanics suggests that these quantum correlations cannot be used to transmit information faster than light, preserving a form of causal protection even in the presence of non-local entanglement. The challenge becomes understanding how instantaneous quantum correlations coexist with relativistic causality in a universe where both phenomena emerge from the same underlying quantum information structure. This reconciliation might require recognizing that causality itself is an emergent property rather than a fundamental law. In the deepest description of reality, there might be no inherent notion of cause and effect, with causal relationships emerging only when quantum information is organized in particular patterns that give rise to space-time geometry and the appearance of temporal sequences. The role of observers and measurement in such a universe becomes fundamentally ambiguous. If space-time emerges from quantum entanglement, and if quantum mechanics requires observers to collapse wave functions and determine measurement outcomes, then observers might literally participate in creating the geometric structure of reality through their measurements and interactions with quantum systems. This observer participation effect would represent the ultimate realization of Wheeler's vision of a participatory universe, where consciousness and observation play fundamental roles in determining the nature of physical reality. The boundary between subject and object, observer and observed, would become blurred in a universe where the act of observation helps determine the geometric structure within which both observer and observed exist. The implications for our understanding of matter and energy are equally revolutionary. If particles are fundamentally quantum information, rather than localized objects moving through pre-existing space, then the entire notion of material substance requires redefinition. Particles would be patterns of entanglement in the quantum information network, with their apparent properties like mass, charge, and spin emerging from the specific ways they are connected to the rest of the universe. This perspective suggests that the distinction between matter and information breaks down at the deepest level. Matter would be a particular organization of quantum information, while information would have physical consequences through its effects on the emergent space-time geometry. The boundaries between physics, information science, and even consciousness studies would dissolve in a unified description based on quantum information processing. The concept of locality itself would require complete redefinition. In a universe where space emerges from entanglement, the notion of local versus non-local effects loses its traditional meaning. All effects would be fundamentally non-local at the deepest level, with locality emerging only as an approximation valid when entanglement patterns create the appearance of separated spatial regions. This redefinition of locality has profound implications for our understanding of forces and interactions. The four fundamental forces of nature might all be different manifestations of quantum information exchange in the underlying entanglement network. Gravity would not be fundamentally different from electromagnetism or the nuclear forces, but rather would represent large-scale, geometric effects of quantum information processing that other forces represent at smaller scales. The unification of forces through quantum information suggests that the traditional reductionist approach to physics, which seeks to understand complex phenomena by breaking them down into simpler components, might be fundamentally limited. Instead of building reality from particles and forces, we might need to understand how complex patterns of quantum information give rise to the appearance of particles, forces, and the space-time within which they seem to exist. This holistic perspective aligns with insights from complexity science and systems theory, which emphasize that the behavior of complex systems cannot always be understood by studying their individual components in isolation. If reality is fundamentally a complex network of quantum information processing, then understanding the universe might require new mathematical and conceptual tools designed for analyzing information networks rather than mechanical systems. The implications for consciousness and the mind-body problem are particularly intriguing. If the brain is a quantum information processing system embedded in a universe that is itself a quantum information network, then consciousness might represent a particular type of information integration that occurs when quantum systems become sufficiently complex and interconnected. This quantum information perspective on consciousness suggests that the boundary between mind and matter might be less sharp than traditionally assumed. If both consciousness and physical reality emerge from quantum information processing, then mental phenomena and physical phenomena might be different aspects of the same underlying information theoretic processes. The hard problem of consciousness, which asks how subjective experience can arise from objective physical processes, might dissolve if both subjectivity and objectivity are recognized as emergent properties of quantum information networks. The apparent privacy of conscious experience might reflect the quantum no-cloning theorem, which prevents quantum information from being perfectly copied and distributed. These philosophical implications extend to questions about free will, personal identity, and the nature of time. If the universe is fundamentally a quantum information processing system, where future states emerge probabilistically from present quantum correlations, then deterministic materialism must be abandoned in favor of a more nuanced understanding that incorporates genuine quantum randomness. Personal identity might be understood as a particular pattern of quantum information that maintains coherence over time through quantum error correction mechanisms similar to those discovered in black hole physics. The continuity of personal identity would reflect the robustness of these quantum information patterns rather than the persistence of any particular material substrate. The nature of time itself would be transformed if temporal relationships emerge from quantum entanglement patterns. The flow of time might reflect the evolution of entanglement networks, rather than being a fundamental feature of reality. The arrow of time, which distinguishes past from future, might emerge from the tendency of quantum systems to become more entangled and scrambled over time. This informational understanding of time suggests that time travel, if possible at all, would be fundamentally limited by quantum information constraints rather than just relativistic causality conditions. The quantum no-deleting theorem, which prevents quantum information from being perfectly erased, might protect the past from modification, even if closed time-like curves could somehow be created. The implications for our place in the universe are both humbling and empowering. If consciousness emerges from quantum information processing in a universe that is itself a vast quantum computer, then human beings might represent local concentrations of information processing capability within a cosmic network of intelligence. This perspective suggests that the universe might be far more alive and aware than traditionally imagined, not in the sense of having a centralized consciousness, but rather as a distributed information processing system where consciousness emerges at multiple scales and locations. Biological intelligence might be just one example of how quantum information can organize itself to create awareness and agency. The search for extraterrestrial intelligence takes on new meaning in such a universe. Other forms of consciousness might exist not just as biological entities on distant planets, but as different types of information processing patterns embedded in the quantum structure of space-time itself. The universe might be teeming with forms of intelligence that operate on scales and timescales far beyond biological comprehension. The long-term future of human civilization could be shaped by our growing understanding of quantum information and its relationship to space-time geometry. If we learn to manipulate quantum entanglement on macroscopic scales, we might eventually become active participants in engineering the structure of reality itself, designing new forms of space-time geometry and creating pocket universes with customized physical laws. Such capabilities would represent the ultimate expression of human creativity and intelligence, transforming our species from passive observers of natural law to active co-creators of reality. The ethical implications of such power would be profound, requiring wisdom and responsibility on scales that dwarf any previous human endeavor. The discovery that gravity and entanglement are connected would thus represent not just a triumph of scientific understanding, but a transformation in humanity's relationship with the cosmos. We would learn that we are not isolated beings struggling against an indifferent universe, but rather patterns of consciousness embedded in a vast network of quantum information that connects everything to everything else at the deepest level of existence. As we reach the end of our journey through the mysterious landscape where gravity meets quantum entanglement, we find ourselves standing at one of the most extraordinary moments in the history of human understanding. Never before have we been so close to grasping connections that could fundamentally transform our comprehension of existence itself. Yet never have the challenges seemed so daunting or the implications so profound. The scientific evidence we have explored paints a picture of a universe far stranger and more beautiful than our ancestors could have imagined. From Einstein's geometric description of gravity as curved space-time to the mysterious non-local correlations of quantum entanglement, from the information paradoxes of black holes to the possibility that space-time itself emerges from quantum information, we have traced a narrative that challenges every assumption about the nature of reality. What emerges from this exploration is not a definitive answer to the question posed in our title, but rather a roadmap for the most important scientific adventure of our time. the connection between gravity and quantum entanglement remains tantalizingly just beyond our experimental reach, supported by elegant theoretical arguments, but not yet confirmed by definitive observations. We stand at the threshold of discovery, with the tools and concepts needed to finally answer these fundamental questions within our grasp. The theoretical frameworks we have examined each offer pieces of what may eventually become a complete picture. Loop quantum gravity suggests that space-time itself has a discrete quantum mechanical structure at the smaller scales, with entanglement between geometric degrees of freedom determining the connectivity and smoothness of space. String theory proposes that entangled vibrations of fundamental strings give rise to all particles and forces, including gravity, in a higher dimensional arena where geometry and quantum mechanics naturally unite. The holographic principle goes furthest in making entanglement fundamental, suggesting that space-time geometry emerges from patterns of quantum correlations in lower dimensional quantum systems. The ER equals EPR conjecture provides a concrete realization of this idea, proposing that every quantum entanglement is literally a geometric connection through space-time, mediated by microscopic wormholes that exist in the quantum foam of reality. These theoretical insights have converged with experimental advances that bring laboratory tests of quantum gravity within sight. The Bose-Marletto-Vedral protocol for detecting gravitationally induced entanglement represents humanity's best hope for directly testing whether gravity operates according to quantum mechanical principles. While the technical challenges remain formidable, requiring unprecedented control over quantum systems and extraordinary sensitivity to gravitational effects, the rapid pace of technological development suggests that such experiments may succeed within the coming decades. The cosmic laboratories provided by black holes, neutron stars, and the early universe offer complementary approaches to understanding quantum gravity through astronomical observations. Gravitational wave detectors have already begun to probe the strong field regime of general relativity, and future improvements in sensitivity may reveal quantum signatures in the gravitational waves produced by merging black holes, or the quantum fluctuations that seeded the structure of the universe during cosmic inflation. The potential applications of gravitational entanglement, should it prove real and controllable, stretch the boundaries of imagination while remaining grounded in the mathematical structure of quantum mechanics and general relativity. From quantum computers that use gravitational fields to entangle qubits across arbitrary distances to communication systems that operate through the quantum structure of space-time itself. From precision sensors that detect the gravitational signatures of dark matter to propulsion systems that manipulate space-time geometry. The technological implications could be revolutionary. Yet perhaps the most profound implications are not technological, but philosophical. If gravity and entanglement are truly connected, it would mean that the universe is fundamentally more interconnected than classical physics ever suggested. Every particle would be connected to every other particle through the quantum information network from which space-time emerges. The apparent separateness of distant objects would be revealed as an illusion created by patterns of quantum correlation that organize reality into the familiar forms of space, time, matter, and energy. This vision of reality as a vast network of quantum information has implications that extend far beyond physics into questions about consciousness, free will, and humanity's place in the cosmos. If consciousness emerges from quantum information processing in a universe that is itself a quantum information network, then the boundary between mind and matter, observer and observed, becomes far less clear than traditional materialist philosophy suggests. The journey we have taken reveals science at its most ambitious and speculative, grappling with questions that touch the very foundations of existence. We have seen how ideas that begin as mathematical abstractions in the minds of theoretical physicists can potentially lead to technologies that transform civilization and philosophical insights that reshape our understanding of what it means to exist in this universe. The story of gravity and entanglement is still being written. Every new experiment that pushes quantum systems to larger scales, every advance in gravitational wave astronomy, every theoretical insight that connects previously disparate phenomena brings us closer to understanding whether these two pillars of modern physics are truly unified at the deepest level. What makes this quest particularly exciting is that it represents one of the few remaining areas where individual human insight and creativity can still make transformative contributions to our understanding of nature. Unlike many areas of contemporary science that require massive international collaborations and billion-dollar facilities, the key insights about quantum gravity and entanglement often emerge from the contemplation of individual theorists working with nothing more than pen, paper, and profound intuition about the mathematical structure of reality. The next breakthrough might come from a graduate student working late in a university library, suddenly realizing how to reconcile the apparent contradictions between quantum mechanics and general relativity. It might emerge from an experimental group that finally achieves the exquisite control needed to detect gravitational effects on quantum systems. It might arise from astronomical observations that reveal quantum signatures in gravitational waves or cosmic microwave background radiation. Wherever it comes from, such a breakthrough would represent one of the greatest intellectual achievements in human history, comparable to the development of quantum mechanics and general relativity themselves. It would complete Einstein's dream of a unified field theory while revealing aspects of reality that even Einstein could not have anticipated. The implications would ripple far beyond the physics community. Educators would need to develop new ways of teaching students about a universe where space and time emerge from quantum information. Philosophers would grapple with the meaning of existence in a reality where consciousness and physics are intimately connected. Engineers would begin the long process of learning to harness quantum gravitational effects for practical applications. Perhaps most importantly, humanity as a whole would need to absorb the profound shift in perspective that comes from recognizing our universe as a vast quantum information processing system, where consciousness, matter, and geometry are all manifestations of the same underlying quantum mechanical reality. This shift could be as significant as the Copernican revolution that displaced Earth from the center of the cosmos, or the Darwinian revolution that connected humanity to the rest of the biological world. As we look toward the future, we can be confident that the questions explored in this journey will be answered, though we cannot predict whether the answers will confirm our current theories or reveal entirely new principles that we have not yet imagined. The universe has repeatedly surprised us with its depth and beauty, from the quantum mechanical nature of atoms to the expansion of space itself, and it seems likely that the connection between gravity and entanglement will provide surprises of its own. What we can say with confidence is that this quest represents science at its most fundamental and most human. It embodies our species' deepest drive to understand the nature of existence, to find patterns and connections that reveal the underlying unity behind the apparent diversity of natural phenomena. Whether gravity and entanglement are truly linked or remain forever separate aspects of reality, the journey to answer this question will advance human knowledge and transform our understanding of the cosmos. In the end, the story of gravity and entanglement is the story of humanity itself, a species that arose from quantum mechanical processes in a universe governed by gravitational forces, now capable of contemplating the deepest connections between these phenomena and perhaps even learning to harness them for purposes we can barely imagine. We are quantum beings in a gravitational universe, and the threads that connect these aspects of our existence may prove to be the very fabric from which reality itself is woven. The universe awaits our discovery of whether its deepest threads are indeed quantum entanglements that span the cosmos, connecting every particle to every other particle in a vast web of invisible correlations that give rise to space, time, matter, energy, and perhaps even consciousness itself? The answer to this question may well determine not just the future of physics, but the future of human civilization and our understanding of what it means to exist in this strange and wonderful cosmos we call home.